This is the lecture for Chapter 3 of your textbook entitled Understanding Structure. Some of the things that we'll be talking about today is what is structured and unstructured code. Often unstructured code is referred to as spaghetti code. We'll see why that's the case later. We'll talk about three basic structures from which any program could be written. That is sequence structures, selection structures, and looping structures. We'll talk about what priming input is and why sometimes you need it to keep your program structured. We'll talk about why we need structure. We'll talk about recognizing and structured or unstructured program. And we'll talk about how we take something that is unstructured and convert it to a structured program. One of the things we talk about is spaghetti code. Basically what spaghetti code means is you have flow errors that go all over the place, and we don't have a good structure from which we can use normal constructs such as looping. It makes the program complicated to follow. If it's complicated to follow, there's more likely that you'll have bugs or that somebody will get really frustrated if they have to go in and try to figure out what your program is doing so that they can modify it. These last two definitions are kind of circular in my opinion. A structured program is one that follows the rules of structured logic. An unstructured program is one that does not. So we'll learn what makes a program structured, and if it doesn't follow those rules, then you would consider it unstructured spaghetti code. So here's an example that relates to washing a dog that we'll see several times. And basically we have arrows that go all over the place. One of the things that you need to do is anytime you have a flow of control that goes back up and hits the code that you've potentially already executed, that code needs to be right above one of your decision diamonds. We'll talk about that over and over throughout the chapter. So a structure, singular, is a basic unit of programming logic. So sequence structure is the easiest, and that's really what we started out when we were looking at this in Chapter 1 and 2. Basically, we just go down the line doing one thing after another, and there are no questions that are asked, no decisions to make, no looping. If we need to do selection, we usually do that with an if-then-else statement. So what that does is it allows you to ask a question. If something is true, then we execute a block of code. If it is false, else we do everything that's in the else block. You don't always have to have an else block. If you just need to do one thing, you can say if this condition is true, then execute this statement or groups of statements. So when you only have if-then, that's referred to as a single alternative if. If you have an if-then-else where you need something if it's true and another block of code if it's false, that's called a dual alternative if. A looping structure is one that just allows you to take a set of code, which we'll start calling a block of code, and loop over it, that is, execute it over and over again based on some condition or sets of conditions. Going back and looking at the three basic structures, here's a flow chart of what a sequence structure would look like. It is one or more process boxes, one after the other, with flow of control just going straight down. A selection structure looks like this. It is implied that this is a dual alternative statement because you ask a question. If it's true or the answer is yes, you would execute the right side of the structure. If the answer is false or no, then you would execute the block or blocks of code that were on the left of it. So in pseudocode, this is what if statements look like. If, and then what condition. If it's true, then do one process, else do another process. So I think in one of your homework assignments, you had to do something while a condition was less than 500. So if you were checking for 500, in that case you'd probably use a loop, but you could say if x is less than 500, then do process 1. Else, that means it is 500 or greater, do the other process that's shown here in the pseudocode. In the case that we do not need the else clause, instead of saying if employee belongs to a dental group, then deduct $40 from their pay, else do nothing, or set their pay to what the pay is already set to. That's just redundant. That would not be necessary. In the first case, when I said else do nothing, that is referred to as a null case. That is, we have a case where we would have an else, but we would do nothing. And in that case, we simply just drop the else clause. There's no reason to put else nothing. In a flowchart, this is what it would look like. If the condition is yes, we take the right branch, we execute whatever's in the process box. If the answer is no, then we would go to the left and just continue the flow of the program to the part of the flowchart below this decision structure. A loop structure, as I said before, is one that just continually loops while a condition remains true. Other terms for this are repetition or iteration. In my experience, looping is where you do something and you say while x equals 500, you need to do some things. In the case of iteration to me is for a value of I from 1 to 10, incrementing by 1 each time, do this set of statements. So in the case of iteration, you're changing a loop variable, and as long as you don't do something that would be considered bad programming style, in the example I gave you, then I would be 1, then I 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a while loop or a while do loop, and those are different in languages. So in this case, we ask a question. If the answer is yes, we execute a block of code. Then we go back and ask the question again. If the question is still yes or true, then we execute the block. So we have a loop there where we just circle until the condition becomes false. That is, the answer to our question is no. And at that point, we drop out of the loop and we continue on with whatever was after this loop structure. So here's a couple of examples. While some condition is true, do some process. The one below has 2 steps. While you continue to be hungry, take a bite of food, determine if you're still hungry, and then, if you are hungry, keep looping. So those are 2 examples of while loops. We put the while, then the condition, then we have the keyword do, and then we have whatever steps we need to take. And then when at the bottom of the loop, we have the end while statement. All logic problems can be solved using the 3 structures we just talked about: sequence, selection, and looping. You can combine these together. You can put selection statements within loops. You can put multiple process statements within sequences, or you can put those sequences with multiple processes in loops. So you can just combine those to solve the logic of your problem. This is referred to as stacking structures. That is, just putting structures one after the other end to end. The end structure statement tells you when you're done. So in the case of process, we would just stop having processes boxes. But in the case of if, then, else, we have the keywords potentially if, then, and else. And then we have an end if. So if we have if, then, some statements in an end if, that only has the true condition. If we have a true and false blocks we need to execute, then it would be if, then, else, end if. And for a while statement, you would have an end while. So here, in both flowchart form and pseudo code form, you'll see, we'll look at the flow chart. We have a sequence, which is step A and B. We then have selection, which is checking a condition and executing one of the two branches. And then after we come out of that, we have a loop that is going to loop while condition F is true. So they've taken one sequence, one selection, and one loop and put them end to end. In the top right of the figure, it shows you what the pseudocode for that would look like. Any individual task you might have, like a process box, can be replaced with an entire structure. If we put one structure within another, if we have a while loop within a decision structure, then that would be referred to as nesting. So we have stacking, end-to-end, nesting, putting one within another. When you nest structures, when you're writing code or when you're writing pseudocode, you're going to indent the statements so it's very clear to yourself and to someone else looking at the program that, you know, hey, I have a while loop within an if statement or something like that. It makes it a lot easier to follow. A block of code, I used that term a few slides ago, refers to a group of statements that are executed as a single unit. So if you say, if the condition is true, then I want to do these three statements, those three statements is referred to as a block of code. So just by coincidence, that's exactly what they're showing here. As far as the flow chart, if the condition is true, I execute a block of code. The block of code consists of step J, step K, and step L. And then they show you over in pseudocode what that would look like. Here we have a nested structure. We have a condition. The false condition or the no condition is a null branch. But over at the left, we have a sequence followed by a loop, followed by another process step or a sequence step. If you will, look at the pseudocode in the top right. Notice how the if is indented a few spaces, and then within the while loop, any step that's part of the while loop would be indented another 3 spaces. This makes your code very readable, and if you have syntax errors or even logic errors, it's going to make it a lot easier for you to look through your code and figure out what you might have done wrong. Here's another flowchart that has selection within a loop, within a selection, or within a sequence of a selection. So you can see how that flowchart is. Notice that it is structured because when we go through condition O, when we circle back, we come right in right before a decision point, which is the checking of condition M. And also note the indentation in the pseudocode in the top right of the screen. Structured programs have the following characteristics. We only use combinations of the 3 basic structures that we were just talking about. Each structure has only a single entry point and a single exit point, and structures can be stacked end to end with the exit point of one being connected to an entry point of the next one. And again, any structure can be nested within another structure, and we still consider that a structured program. Now, one problem we have, and we'll see a flowchart of this, is kind of getting the first value in, or the first line of input, and get it dealt with correctly. And one way to solve that is with something called a priming input or possibly a priming read. The reason it would be called a priming read is a lot of times you're reading that value from the user or you're reading that value from an input file. So it reads the first record outside the loop, and then you have a loop that decides whether to process that line and then handles the reading and processing of future lines. So we will look at that in a moment. Again, in the case of structured code, We ask a question, we take action based on that answer, and then we return to ask the question again. So they're saying if it does not follow those 3 steps, or those 3 in order specified, then we have an unstructured program. So right here, at first this looks like a structured program, and it actually is a structured program, because when we take the yes branch of not end of file, we go back right above that decision point. So that makes the program structured. Now the problem is we have a logic error. If you follow this, I read a number from the user, I verify that the value is not end of file, and if that's the case, I double the value, I output the answer to the user, and then I circle back up and say, hey, am I not at end of file? No, I'm not. Okay, let's take the original number and multiply it by 2, output that. So we never change the value of original number. So this program is going to be an infinite loop that just keeps printing out the same answer over and over again. So it's structured. They say non-functional. I'm going to say it has a logic error. Now then, so somebody's looked at this and said, oh, yeah, I need to read the number over and over again. So let me return out of the true branch of my decision above the input original number. Now, because we have input original number, before the decision point, this logic is not structured. We would need to come in before the not end of file. So what we have to do to fix this is, looking at this flow chart, notice that they've used the annotation symbol a couple of times. It's important that you know that. It's important to know that's basically the flowchart way of doing what we would call in program code or pseudocode comments. So what they do is they get the first number. If that first number is not end of file, then they calculate an answer. They output the answer, and then they need to get another number, and then go back and say, okay, is the most recent input I got end of file? If it is, then I would stop. If it's not end of file, then I would continue looping. Now, one thing that they don't point out here that I would definitely comment on your program and down the road potentially take points off is, last lecture we talked about meaningful variable names. So they declare calculated answer. That's fine. It's an answer that we're calculating. But notice that the other variable they call original number. So the name original implies the first number. So I would argue that the first time you read a number that was the original number, but when you came back and got another number, that's not necessarily something you would call an original number. So inputted number, user's number, something like that would probably be a much better variable name instead of original number. Here's another one where, quick glance, this appears to be structured. This might be the way you change to do this, but what happens is, since you have a sequence of steps on the right, when it goes through and says not end of file, we learned last time that uninitialized variables are set to garbage. A random garbage value would probably not be end of file, so we would go down the true branch, the yes branch. We would get a number from the user, and then we would double it and we would output it. So at first glance, you probably think, yeah, that makes sense. That seems reasonable. But the problem is when you input or attempt to read the number, if the user says end of file, it's going to try to multiply that end of file by 2, and then it's going to output whatever that is. So that may generate an error message, or it may generate what appears to be some random value. So if we try to solve it this way without priming the loop, we're going to have problems, and we're going to get extraneous output. So you probably figured some of these out from the lecture so far, but the reasons we care about structure is, first of all, clarity. If we have spaghetti code that jumps all over the place and the flowchart's a real mess, the pseudocode would even be harder to write. It's not going to be very clear. So if we use structured constructs in making our program, it'll be much clearer. There'll be clarity. As far as professionalism, other programs expect it. If you are a good programmer, you're going to write structured code. If you happen to not write structured code and you give it to somebody else or show it to somebody else, they may look negatively on you because the assumption is you don't know how to write structured code. Most languages support a structure. There are some really old languages where it would be really difficult to do things like looping. Basically, you read all of your input, you do all your calculations, then you do all of your output. But most modern languages, if not all modern languages, will allow you to write code that match up with these three structures. As far as maintenance, they say other programmers. I always say if you haven't looked at a program for a year or two and you come back to look at a program, it'll apply to you as well. But basically, it's going to be much easier to read and much easier to understand if you follow the rules of structure. The other thing, too, is if you follow structure, it makes it a lot easier for you to pull some chunks of code and decide they need to be in a module and modularize your program based on that. So if you have spaghetti code, it's going to make it more difficult to pull out sections of it and modularize. So here's an example of a couple of structured flowcharts. In both cases, we come back to the point above the decision point in example 2. And example 1 is just a sequence statement followed by a conditional if statement, so a decision structure. So yes, these are fine. Now, if we look at the top figure that is not numbered, the top left in the box, notice that we just kind of go all over the place, and we have 2 decision points up there. So if we break it down, step G is fine. If we add H to that, that's fine. If the answer is no, we need to execute block J. If the answer is yes, then we need to answer another question, is I true or false? And in 5, what we need to do, instead of connecting the no of the I condition to the no of the H condition, we just need to repeat the statement. We need to say if the answer is no, then we need to do J. If it's yes, then we need to do K. And then we would connect all those together and continue on to whatever the next statement or next step might be in our flowchart. Looking at the dog washing program, in the first case, we start down with number 1, trying to catch the dog. So we're kind of in this loop here trying to catch the dog. Now what happens is if we catch the dog, we turn the water on. If the dog runs away, we come back up to the top decision point instead of the bottom decision point. This would probably still work. At quick glance, I think logically it would work, but it is unstructured because we have a branch of a loop. The second does the dog run away, instead of returning to right above that decision point, it goes up to the top decision point. So what you would need to do is do what they've finally done in 3, which was have the loop, the second does the dog run away loop. And then we would continue on with the logic of the program if there was more that we needed to follow. So our end program ends up looking like this. So a lot of times recognizing structure is a lot easier if we look at the flow chart, because basically, do we return right above the decision point? And on the left in that flow chart, yes, we do. Over at the right is the matching pseudocode. Again, I can't stress enough, you need to come up with a good indentation style. I personally like to indent 3 spaces. Looks like they like to indent 3 spaces. The exact number does not matter. The point is you have to have indentation, and that indentation needs to be consistent throughout your pseudocode. Or when we start writing code, it'll need to be consistent within your program code. We talked about making it easier to modularize. What they've done is they've somewhat abstracted some of the steps. Again, a rectangle with that extra line at the top is an internal module. I think we learned about that in Chapter 2. That means the code for that module would be within the code of the main program, as opposed to if there were double lines on the left and right of the box, that would be an external module, which would mean that code exists somewhere else in a different file than our main program. So what they've done is they have a module called Catch Dog Start Water, and there are 3 places they can call that code. So we're reusing code. Let's say Catch Dog Start Water is 5 or 6 steps. We could put the 5 or 6 lines of code in each of these locations, but that makes our program longer. It's probably clearer to have a little bit of abstraction where somebody can just look at the name and say, oh, we're going to catch a dog and start water. And then if I need to know the exact steps to do that, then I could look in the module's code. The other thing that I don't think your textbook mentions, but is very, very important, is let's say each one of these is 6 lines of code. And I write my program and I need to enhance it, or I determine there's a bug and I need to go back and fix it. What if I only change it in the first block of code and the second block of code and forget to do it in the third location that is highlighted? So then I have code that's supposed to do the same thing but does not, because I forgot to correct the third mistake. In the case of having one module that you call multiple times, you make the change in the module, and then it works correctly everywhere you might access that module within your program. So that's another big advantage that they don't mention. So that finishes up Chapter 3. Avoid spaghetti code, know how to identify well-structured and unstructured code, realize what sequence selection and looping is, know that all programming problems can be solved using just these 3 constructs, and that stacking is putting one of these structures end to end with another structure. Nesting, as the name implies, is putting one structure inside another structure. All those are acceptable. And then it is important to understand what priming input is, which is basically getting one value before you go into a structured loop to keep it structured and so that the logic of your program works correctly.